Alright, hello. So here we are for part 3 of lecture 4 of CENG 4412 Steel and Concrete Design. So for the last portion of this lecture, what I would like to do is just work through this design example, or analysis example actually, applying the equations we've learned previously to calculate yield strength and yield and fracture strength for both tension members and connecting elements. Alright, so let's begin. I know this is kind of late. Recording this at, starting this at 10 p.m. On a Monday evening, and have a 8 a.m. lecture for the same class, actually, 4412 tomorrow morning, but oh well, such is life. We can sleep when we're dead. Okay, so this is going to be our example problem. In the previous portions of this lecture, we have gone through and work through all of the equations and the theory, etc. But I just want to work through a sort of relatively long form example problem. Now, first of all, let's look for this example problem. I will do a traditional sort of given find solution format. Given. And first of all, in this slide, this is going to show the geometry therein. So this is going to be your geometry. Now, let's look at what's happening here. We have a connecting element, which is a set of angle irons, 6 by 6 by 3/8. So that means, again, if you're not familiar with your L shapes, that we have a L shape. This is, again, called an L shape. It is 6 inches long by 6 inches long by 3/8 inches thick. And we also have we have a set of these things, and they are bolted around a gusset plate that is then connected to a fixed connection. And this fixed connection could be a number of things. It could be a column, it could be a beam, it could even just be a foundation directly if you somehow have a tension element connected directly to a foundation slab, maybe in some sort of bridge abutment or bridge pier or something like that. Anyway, so here, this slide basically shows all of our geometry. This is sort of just a big slide for all of our problem geometry. And make sure we're recording, we're good. Then, so I do want to list a few things. Now, a lot of the things we do in terms of our tension members, so again, tension members are our long, slender elements. They are the in a frame structure, they're the things you see the most. In this case, our angle irons, our L shapes, are our 6 by 6 by 3/8. And a single L, if you ever see something labeled as a just L 6 by 6 by 3/8, that would refer to just a single angle iron here. A LL refers to 2 angle irons joined together back to back. Okay, but we'll need a few bits of geometry here. First of all, we want to get our section properties, and these are found in, again, Chapter 1 of the AISC Steel Manual here. And for angle irons, I find these in Table 1-7. Table 1-7 for L shapes or angle irons. They're called angle irons because they're kind of like an angle, or L shapes because they form the shape of an L. But for this particular one, for L 6 by 6 by 3/8, see page 1-46 of the 15th edition. Okay, so we will need a few things. First of all, if you remember previously, we need to look at our X bar. Our X bar is going to be important for some later calculations, and that is the distance from the centroid of an angle iron here to the connecting plane. And you can find that labeled in the table. And so this is our X bar, and for this particular shape, and it's going to be different for every single type of angle iron that you find in the catalog or in the manual. But for our particular one here, X bar is equal to 1.62 inches. So that's one particular section property that we will need. And then another one that we'll need that we'll find in this section of the code is the gross section area. And the gross cross-sectional area again, if we look on page 1-46, we see that for one of these shapes, for the L, for the angle iron L 6 by 6 by 3/8, it is 4.38 inches. Uh, 4.38 inches. And that means for both of them, though, if we combine them together, for both, because again, we have two of these things here, and so then for two of them, the total gross cross-sectional area is going to be a bit larger. And so our overall AG, when designing for our tension members, AG is going to be 8.76 square inches. 8.76 inches squared. And in line with this as well, so we now have our gross cross-sectional area, and let me label that a little bit better. That's a little bit messy. Kind of writing on the edge of the table here. 8.76 inches squared. And if you remember previously, we calculated our a factor that was 1 minus x bar over L, or 1 minus x over L. And the L here is the length of the connection. And for a weld, if you had like a longitudinal weld, it would just be the length of the weld, the length of the weld from start to end, or from beginning to end, start to finish, etc. For a bolted connection, your length of your bolted connection is the length from it's a center to center distance from the first bolt to the final bolt. So if we have 4 bolt holes or 3 bolt spacings, each at 3 inches, our total connection length is going to be 9 inches. So our 1 minus x bar over L is going to be our 1.62 inches from here. So 1 minus 1.62 here, divided by 9, which will then equal 0.82. 0.82. Now, what else? So I do want to do a little bit of review of the load path here. So P ultimate, that's going to be our ultimate load, our ultimate factored load. Then we're going to have the, so that load is present within the tension member, within our set of angles here and here. Then it's going to transfer into the bolts. The bolts are going to transfer that into our gusset plate here, our 1/2 inch gusset plate. And then that's going to be transferred into our fixed connection here. Now again, this fixed connection could be any number of things. It could be a column, it could be a beam, it could be a foundation. For our purposes here, we don't care what it is. It's just a simple fixed connection. For the sake of our calculations here, we effectively consider this to have infinite strength. Okay, so on this slide here, I am laying out some given geometry factors. On this slide here, I'm going to lay out some givens for material properties and loading. So given material properties and loading. Material and loading. Material, loading, and assumptions. And assumptions. So, let's see here. This is more of a material property. 1, the gusset plate is A572, grade 65 steel. And so that knowing that fact will allow us to determine both the yield and ultimate strength. 2, the tension member is A36 steel, so good old fashioned A36 30 KSI yield strength steel. 3, the loading. Well, we have a dead load equal to 35.5 kips and a live load equal to 106 kips. 106 kips. And we are told the following do not apply. Well, I can actually just say the limit state of block shear rupture does not apply. And the reason for that, well, if you're actually designing or calculating such a connection, or I shouldn't say calculating, designing or analyzing such a connection in the real world, you would not want to assume this. But for this sake, for this particular problem, we have not gone over block shear rupture yet. So if you want to provide a quote-unquote rational reason for how this might apply, well, yesterday you met a magical genie, and the magical genie gave you 3 wishes, and for some reason you said, I wish that whenever I design a steel connection from this time forward, block shear rupture will never apply to that connection. Perfectly rational reason. Okay, so the limit state of block shear rupture is not rational because of our magical genie friend and our total waste of a genie wish. Block shear rupture does not apply. Even if you're only trying to avoid doing math and hard work, compared to some of the things we'll see in bending, if you're going to waste a genie wish on a limit state, block shear rupture isn't a good one. Anyway, but for now, we'll just say the block shear rupture does not apply. And here, this is an unstaggered bolt pattern. Unstaggered bolt pattern. So again, I don't know if we discussed this previously, but staggered versus unstaggered. Staggered means that the different rows do not align along the column line. So for example, imagine if I took these 4 bolts and move them over a bit. So take these 4 bolts here and in your mind move them over. So like this bolt here is here, this bolt here is here. That would be a kind of staggered connection. This is an unstaggered connection where the individual rows line up appropriately. Now, in later lectures, we'll see why staggered bolt connections can be beneficial, but they do make the analysis a bit more complicated. So we'll assume this is an unstaggered bolt connection, but that should be apparent from the drawing. And also, we're going to assume that welds and bolts, the fixed connection and bolts are adequate. And bolts are adequate. So back here, again, block shear rupture, we don't need to worry about that because the magical genie took care of that. And in terms of the fixed connection, that's when we actually design things in the real world, we have to start worrying about, well, is the weld strong enough to hold the gusset plate to the fixed connection? And is the fixed connection actually, whatever that thing is it a column, is it a beam, is that actually strong enough to withstand this loading? Well, let's just say the magical genie isn't involved, but the weld material and whatever this thing that it's connected to, they're both made of adamantium just for fun, so they have infinite strength. We don't need to worry about them. So problem solved. Again, this problem is very much, this design example, or this analysis example, is very much a simplification. Okay. Moving on here. Let's see here. And I might need to pause it really quick because this seems to have crashed. Actually, no, I'll just keep going. Let's see. I think, unfortunately, PowerPoint seems to have crashed. Let's see here. Oh, I may have lost those notes, but it's still recorded, so it's all good. This is not my first take on this, but let's just keep moving forward. Actually, let's see if I got this. I may have. Let's see. Nope, I seem to have lost those notes, but we got it recorded, so we'll just keep trucking on. Okay, thankfully we got it recorded, so we don't need to repeat that. Okay. So, the first step, again, we have all our givens. Let me make sure we're still recording. Here we are. So we have all of our givens. So let's next look at our load cases. Well, we have our givens. Let me go ahead and write the word solution just to keep things really formal. My computer doesn't seem to like working late at night either. And let's look at our load cases. Load cases. The first load case that I'm going to look at is 1.4 dead. And the second one would be 1.2 dead plus 1.6 live. Now, again, in the real world or in real design problems, or really real design cases, we would look at additional load cases involving snow load, wind load, etc., roof live load, earthquake load, everything else. But in this case, we were only given 2 loadings, so we know that one of these 2 is going to control. So 1.4 times 35.5 kips, and this is going to be equal to 49.7 kips. And 1.2 dead plus 1.6 live is going to be equal to 1.2 times 35.5 plus 1.6 times 106. And this will be equal to 212.2 kips. 212.2. Now again, in most real cases, real world cases, you're going to have a case 3, a case 4, etc. But for our example here, we are only given 2 loadings. We've simplified this a bit. I just wanted to provide these as a reminder of how you actually calculate factored loads. So in this case, this one will govern. Governs, really? Governs. We need an R there. Governs. Okay, so in other words, in terms of our more generic equations, our sigma phi qi would be equal to 212 kips. And so this is our demand. And now we need to make sure that both our tension member and our connecting element are capable of supplying enough resistance to meet this demand. So let's first look at the tension member and the tension member limit states. Again, the tension member would normally have block shear rupture to consider, but the magical genie took care of that, so we don't need to worry about that for this particular lecture. So tension member limit states. All right, so first of all, we're going to look at yielding. We're going to again look at both yielding and fracture. Yield. And our governing equation here is phi Pn is equal to phi Fy Ag, where Ag is our gross cross-sectional area. And this is, as a reminder from previous videos, this is equation D2-1 on page 16.1-28 of the 15th edition. Then numerically, this is going to equal 0.9 times 36, 0.9 times 36 KSI times a gross cross-sectional area of 8.76 square inches. Again, we have 2 of these angle irons, and this gross cross-sectional area is the combined cross-sectional area of both of them put together. And so that will equal 283.8 kips. 283.8 kips. And so then we need to get, this is our sort of our nominal, or well, this is actually our factor resistance. And here, and so basically we need to be in all cases sure that our phi Rn, or sorry, phi Pn, is greater than our, in other words, we need to make sure that our factored resistance is greater than our factored load. So, factored resistance must be greater than or equal to factored load. So, phi Pn, we already calculated it as 283.8 kips. And this must be greater than or equal to our previously calculated P ultimate of 212.2 kips. And indeed it is. So therefore phi PN is greater than or equal to P ultimate. So in terms of yielding on the tension member, we are good. No problem there. So next we need to move on to fracture. So at least in terms of yielding on the tension member, again, we lost some slides because of the PowerPoint deciding to crash out on us. But in terms of yielding on the tension member, the yielding on these angle irons themselves, we are good. All right, so continuing on, let's look at the fracture strength of the tension members. Okay, so we've already calculated the yield strength. Now let's look at the fracture strength. Okay, so fracture for tension members here. Fracture for tension members is governed by the equation phi p nominal, or in other words, our design strength is going to be phi fu area effective. Area effective, where area effective, and for the exact equation citation on that, please see the first portion of the lecture, where area effective is equal to U, the shear lag factor, times AN, the nominal cross-sectional area. Then, again, U, we've already calculated that previously. That is 1 minus x bar over L, and we calculated that as equal to 0.82. 0.82. Then AN is equal to AG minus area of the holes. So the gross cross-sectional area minus the area of any holes present. And for our example here, this is going to be equal to 8.76 square inches minus the diameter of the bolt plus 1/16 plus 1/16 times the thickness times the number of the holes. Now, for this particular problem, because we have two different angles joined we have two different angles joined together, we're going to have to multiply the thickness of our 3/8 inch angle iron by 2. So this is then 8.76. I will annotate this a bit. Inches squared. Then, if I again, as a reminder, the first 1/16 is due to the extra space needed for the bolt hole, and the second 1/16 is due to damage that occurs in the underlying plate as you're drilling the hole. But if you combine those together, that comes to 1/8 inch minus 7/8. So the diameter of the bolt over here was 7/8 inch. Then 7/8 inch plus 1/8, 1/8, times the thickness, which is 3/8 inch times 2, and then the number of holes is going to be 2. So overall, our net area is 8.76 inches squared, and all of this here comes to 1.50 inches, or square inches, I should say. 1.50 square inches, approximately, and that comes to an area, a net area of 7.01 inches squared. And so, here, just applying this equation, fairly straightforward, our phi PN is going to be equal to phi FU area effective, and our area effective is going to be this number here times our U factor. So this is going to be, again, 0.75. And, or as a reminder from previously, we'll use different load factors depending on whether we're looking at yielding or fracture, etc. For yielding here, we used a higher load factor because that's a more for fracture, we're using a lower resistance factor than yielding because fracture is a more critical failure state or failure mechanism. It's much worse if something fractures or breaks in half than if it just yields or stretches too much. 0.75 times 58 KSI times our U factor of 0.82 times 7.01 inches squared. And so then that comes to 250 kips. And then that comes to, so we have an overall strength of our of this in fracture of 250 kips. And this is also good. This is not God, this is good. Pardon that. So that's what happens when you do steel design late at night. So anyway, so in other words, we are good in fracture or good in yielding, and good in fracture. And so therefore, our tension member will be adequate. At least from the point of view of this problem. Now, again, we are greatly simplifying the system by just hand waving it away and saying, don't worry, we don't have to worry about block shear, we don't have to worry about bolts, we don't have to worry about welds, anything like that. But we see now that our tension member at least is okay. Okay, so next we need to look at our connecting element, and that'll be the final part of this problem. Connecting element, limit state check. So let's just go down the line. For yield, our governing equation will be phi Rn. We tend to use an R for our connecting elements and a P for our tension members, where phi Rn is equal to phi Fy Ag, and then this is just going to equal to 0.9 times 65 KSI. So we notice our connecting element in this case has a much higher yield strength than our simple 36 KSI tension member. So you do have to use the relevant yield stress and ultimate stress for whatever element you're analyzing at the moment. This is grade 65 steel, so we'll use 65 KSI for our yield stress. Then our area gross is, if you go back here, this is 12 inches long, or tall, I suppose, and 1/2 inches thick. So our gross cross-sectional area is going to be 12 inches by 1/2 inches. By 1/2 inches, or if you multiply all that out, you'll get a value of 315 kips. And 315 kips is much greater than our P ultimate, our ultimate demand load, so we are good in terms of yielding for our connecting element. Good for yielding. Or maybe I can say connecting element, good for yielding. Good for yielding. Next, I want to check our but I next want to check the connecting element for fracture. In other words, I want to check the gusset plates for fracture. So let's look at this, work through our equation, calculations, etc. And phi Rn is going to equal to phi, is going to be equal to phi FU AN, that's an FU A nominal, or A net, not nominal, sorry, A net. And where AN, I said A nominal earlier, apologize, it's a bit late. A net is equal to AG, where AG is the gross area, minus area of the holes, A holes. And so then this will be equal to 12 inches squared, or not 12 inches squared, 12 inches times 1/2 inches, or 1/2 inch. And we do the same kind of diameter of bolt plus 1/8 diameter of the bolt, plus 1/16 plus 1/16 times the thickness times the number of holes. And if you work through all that, you will find that the net area is 5.0 inches squared. Is 5.0 inches squared. So not nominal area, net area. Sorry if I did that previously. Sorry if I said that previously. So then phi RN is 0.75. That's our resistance factor, times 80 KSI. So so we can see here that our gusset plate is made of much stronger material than our tension member, times 5.0 inches squared. And that comes to a value of 300 kips. And if we go back, we remember that our loaded case, we had an ultimate load of 212 kips. So this is much greater than 212 kips. So therefore, this is good in fracture. Connecting element is good in fracture. Then I wanted to do a geometry check that we discussed previously. Geometry check, and that's going to be to check whether it's that 0.85 gross area, whether area nominal is greater than or equal to 0.85 of the whether the here, I want to check to make sure that 0.85 times the gross area is greater than or equal to the area nominal. Or sorry, I did it again. Sorry, late at night. The net area, not area nominal. I see N sometimes. I think nominal, not net. So 0.85 times 12 inches times 1/2 inch must be greater than or equal to our gross area here. And then must be greater than or equal to our nominal our net area. This what we got previously. And so 0.85 times 12 inches times 1/2 inches comes to 5.1 inches squared, which is greater than our net, not nominal, net area of 5.0 inches squared, and we are good there. So good for a geometry check. So again, we just want to check for our connecting elements that are that 85% of our gross area is greater than our net area. So let's do a final slide where we sum things up a bit. Summing up. Maybe I'll do this in blue. That's what I did. That's what I used my main headers for previously. Summary. So here, first, our ultimate loads PU equals RU equals 212.2 kips. Same for both our connecting element and our tension member. And for tension member yield, we determined that phi pn was equal to 283.8 kips. Actually, let me double check that. I modified these notes slightly since last time. 283.8 kips here. That one was okay. It's the next one. It's not quite okay. 283.8 kips. And this is greater than 212.2 kips. So that's good. For tension member yielding. For tension member fracture. Phi pn, and we calculated this as equal to 250 kips, which is greater than 212 kips. I'll just abbreviate this to 212, and so we're good there. Let me mark that 250 in my notes. I found a slight error in my previous notes when I worked through this again tonight. Which is also why I'm working so late. I've done more than one take of this. Connecting elements in yield. Phi Rn is going to be equal to 315 kips, which is also greater than 212 kips, which is good as well. And connecting element in fracture is going to be phi Rn is equal to 300 kips, which is also, that's a really bad K, which is also greater than 212 kips. And so that's also good. So when we combine all of these together, we can finally conclude, after all this, that that everything, the whole system is adequate. Again, though, we want to keep in mind what we're ignoring. So again, for the purpose of this problem statement, we were just given the information that we could ignore a lot of things. We could ignore many different things, but we ignored, let me just remind you all what we ignored. We ignored a few things, and we'll learn about these later in the semester, and some of them even tomorrow. We ignored tension member block shear. Connecting element block shear. We'll explore these later. And bolt strength. And these are some items we'll discuss tomorrow, and well, we'll learn about block shear in this week, and then bolt strength we'll learn about later in the term. All right, that'll do it for this lecture today. I'm finishing up with, again, this is, at 10:40 at night. I'm finishing up lecture 4, which is for last Thursday, but that'll do it for today, and as always, thank you.